Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Edwin Hubble's 1929 publication, A Relation Between Distance and Radial Velocity Among Extra-Galactic Nebulae, stands as a cornerstone in the development of model cosmology. This relatively short paper delivered an observational correlation that reshaped our understanding of the universe, transitioning it from a static, unchanging entity to an expanding cosmos. To fully appreciate the impact of Hubble's work, one must first examine the intellectual landscape from which it emerged, the methodology he employed, the initial reception of his findings, the profound implications that continue to resonate within astrophysics. Prior to Hubble's 1929 paper, the prevailing cosmological model favored a static universe, largely influenced by Albert Einstein's initial formulation of general relativity. Einstein, in his original field equations, introduced the cosmological constant, a term designed specifically to counterbalance gravity and maintain a static solution. This addition, while seemingly ad hoc, reflected the then widespread belief that the universe was neither expanding nor contracting. Willem de Sitter had previously proposed a cosmological model, a static solution to Einstein's field equations, but with peculiar properties including a redshift increasing with distance to the observer, and Vesto Slipher's spectroscopic observations supply crucial. Slipher, working at the Lowell Observatory, meticulously measured the radial velocities of spiral nebulae. These measurements, obtained through the Doppler shift of spectral lines, overwhelmingly indicated that these nebulae were receding from Earth. A significant majority exhibited redshifts, suggesting motion away from our vantage point. While Slipher's data hinted at a systematic recession, he offered no interpretation concerning cosmic distances or relationships. His catalogue of radial velocities provided one vital piece of the puzzle, a puzzle that Hubble would assemble into a coherent picture. Hubble's contribution lay in establishing a crucial link between these radial velocities and the distances to the nebulae. This required him to independently determine the distances to these objects, a significantly challenging task given the limitations of astronomical measurement techniques at the time. Hubble used several distance indicators, primarily Cepheid variable stars. Cepheid variables are stars whose luminosity varies periodically, with the period of their variation directly related to their absolute luminosity. By measuring the period of a Cepheid variable in a distant galaxy, Hubble could infer its absolute luminosity and, by comparing this to its observed apparent luminosity, calculate its distance. It becomes important to outline the method Hubble used to determine the distances to these galaxies. It was through the period-luminosity relationship of Cepheid variable stars that he measured the distance to several galaxies. The period-luminosity relationship, first discovered by Henrietta Leavitt, states that the period of a Cepheid variable is directly proportional to its absolute magnitude. Hubble would identify Cepheid variables in distant galaxies, measure their periods, and then use the period-luminosity relationship to calculate their absolute magnitudes. Knowing both their absolute and apparent magnitudes to estimate the distance to these Hubble's paper presented a plot of radial velocity versus distance for the nebulae in his sample. This plot revealed a roughly linear relationship. The farther away a nebula was, the faster it appeared to be receding. This relationship is now famously known as Hubble's law, mathematically expressed as v equals h0d, where v represents the recessional velocity, d represents the distance, and h0 represents the Hubble constant, the slope of the line relating velocity and distance. His initial estimate of the Hubble constant was significantly higher than modern measurements, approximately 500 km per second per megaparsec. The underlying principle held. The implications of Hubble's law were profound. It suggested that the universe was expanding uniformly, with galaxies moving away from each other at a rate proportional to their separation. This finding provided strong evidence for the Big Bang theory, the idea that the universe originated from an extremely hot, dense state and has been expanding ever since. In effect, it was an observational confirmation of the expanding universe solutions to Einstein's field equations, solutions that Alexander Friedmann and Georges Lemaitre had independently derived but which Einstein initially dismissed, famously calling his introduction of the cosmological constant his greatest blunder. The initial reception of Hubble's paper mirrored the revolutionary nature of its findings. While the evidence for an expanding universe was compelling, some scientists remained skeptical. The large value of Hubble's initial estimate of the Hubble constant presented a challenge. It implied a much younger universe than geological evidence suggested for the age of the Earth. This discrepancy triggered debates and attempts to reconcile the astronomical and geological timescales. Moreover, certain astronomers questioned the accuracy of Hubble's distance measurements, citing potential systematic errors in Cepheid variable calibrations or the presence of unrecognized interstellar extinction. One immediate challenge to Hubble's initial findings came from Walter Baade, who, in the 1950s, demonstrated that there were actually two populations of Cepheid variables, population 1 and population 2, with distinct period-luminosity relationships. This discovery led to a recalibration of the cosmic distance ladder and a substantial reduction in the value of the Hubble constant. Baade's work highlighted a crucial point: the accuracy of cosmological measurements relies heavily on the accurate calibration of these distance indicators. Beyond the immediate refinements to distance measurements, Hubble's work spurred a flurry of theoretical activity. Cosmologists began developing more sophisticated models of the expanding universe, incorporating concepts such as dark matter and dark energy to explain observed discrepancies between theoretical predictions and observational data. The Big Bang theory, initially a speculative idea, gained increasing acceptance as further evidence accumulated from various sources, including the cosmic microwave background radiation discovered by Arno Penzias and Robert Wilson, and the successful predictions of Big Bang nucleosynthesis for the abundances of light elements. Hubble's contributions extended beyond his specific findings regarding the velocity-distance relationship. His meticulous observational approach and his emphasis on empirical evidence played a crucial role in shaping the development of modern observational cosmology. He established a paradigm for using observable phenomena to test theoretical models. Beyond the Cepheid variables, Hubble had contributed significantly to the classification of galaxies. He categorized galaxies based on their morphology into ellipticals, spirals, and irregulars, a classification scheme which, while refined over time, is still used today as the Hubble sequence. He demonstrated that galaxies were island universes, vast systems of stars comparable to our own Milky Way, further solidifying the understanding of the true scale of the cosmos. It is essential to highlight the direct influences that shaped Hubble's work. In terms of direct influence, Hubble built upon the work of Vesto Slipher, who first measured the redshifts of galaxies. Without Slipher's catalogue of radial velocities, Hubble would have been unable to establish the velocity-distance relationship. Another notable influence was Henrietta Leavitt's discovery of the period-luminosity relationship for Cepheid variable stars. This relationship provided Hubble with the tool he needed to measure distances to faraway galaxies, a methodology that has been previously mentioned. The lasting influence of Hubble's 1929 paper is undeniable. Nearly every subsequent advance in cosmology has, in some way, been predicated upon his initial discovery of the expanding universe. The Hubble Space Telescope, named in his honor, stands as a testament to his enduring legacy. This orbiting observatory has provided unprecedented views of the cosmos, enabling astronomers to refine measurements of the Hubble constant, probe the distribution of dark matter, and study the formation and evolution of galaxies with extraordinary detail. The determination of the Hubble constant remains a central goal in modern cosmology. Ongoing efforts to measure this value with ever-increasing precision continue to reveal intriguing tensions between different measurement techniques, potentially hinting at physics beyond the standard cosmological model. Measurements based on the cosmic microwave background radiation obtained by the Planck satellite yield a slightly different value for the Hubble constant, and those derived from observations of Cepheid variables and supernova in the local universe. This discrepancy, known as the Hubble tension, provides a fertile ground for theoretical exploration, potentially requiring modifications to our understanding of dark energy, dark matter, or the fundamental laws of gravity. Despite these ongoing refinements and unresolved questions, Hubble's 1929 paper maintains its status as a watershed moment in the history of science. It ushered in a new era of observational cosmology. It transformed our understanding of the universe from a static, unchanging entity to a dynamic, evolving cosmos. Hubble's meticulous observations, combined with his bold interpretation of the data, continue to inspire astronomers and cosmologists to push the boundaries of human knowledge and to explore the vast, mysterious universe that surrounds us. The paper continues to be a staple during introduction to astronomy courses, serving as an accessible introduction to the field and a prime example of how scientific inquiry can reshape our view of the universe.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.